We are back for P set 5. So we need to look at the phase diagram below, and we need to fill out all sections of the phase diagram. So we know that this phase plus this phase will be this region here, this phase plus HCP alpha here. We're given this here. And actually we can say that TI is this line right here, plus BCC will add up here. This BCC plus this goes here, here, and here are added together, here and here added together, here, and actually let's look at this here. TINZ, and that's liquid plus TINZ here, and we have TINZ2, or 3. So actually we can say that this is TIN3, so this plus this, and we can say this guy plus liquid is up here. This is going to be liquid plus this phase right here. This will be this phase plus whatever this solid phase here, this phase plus whatever that solid phase is here, this solid phase plus basically this solid phase right here. This is a two-phase region, and then this will also be this solid phase here plus that. So again, you know how to fill out the phase diagrams effectively at this point. Now, remember, invariant points. Actually, let's do any congruent melting points. There may be a congruent melting point here, maybe a congruent melting point right here. There's also congruent melting points here and here, as we know from our basically phase diagrams. If we are looking at, and actually this is a little bit of a typo, but we'll figure that out later. Zinc and titanium. Zinc and titanium. So remember, if we have the bunny ears, that is going to be U. So some type of U. If it's an ick, there's liquid involved. If there's an oid, it's only solids. So we're going to go from liquid to a two-phase solid region, or a single-phase solid region to a two-phase solid region. I could also have, these will be peris. And again, ick means a liquid, oid, peritectoid will be basically solid regions. So again, this could be liquid to alpha plus beta. My mistake here. That's not true. We can look at a liquid plus alpha goes to a beta phase here. So a two-phase region into a single-phase solid region. So let's go ahead and look at what are the invariant points we have here. This is a eutectoid. We have the bunny shape, right? Solid to two-phase solid region, that's an oid. What about here? We have BCC plus, so this is solid region to a new solid phase right here. So that is also going to be that's going to be a peritectoid. What about right here? Liquid to solid here plus solid here, that's going to be a eutectic right here. So let me kind of erase that. Hard to see, but you can kind of deduce that. Same thing here. Liquid to two-phase solid region, eutectic here, eutectic right here as well. What about right here? This is a single-phase solid region solid plus liquid to another solid phase right here. That is a peritectic. Liquid plus solid to new solid, peritectic here as well. What about here? Solid plus solid to a new solid, peritectoid. What about here? Solid plus new solid, solid to new solid, peritectoid. There we go. That's it. Those are the invariant points on this phase diagram. So let's continue. Consider composition of mole fraction 0.55 zinc. So 0.55 would be probably about right here at 1220 K. So let's do 1220. So let's just say approximately, let's add it a little. Let's go probably let's say right here, roughly. So let's say we're right here. Excellent. So my C naught is equal to 0.55. My composition, I'm in a two-phase solid region, right? So there's going to be some composition that's ZN, that's titanium, zinc. And there's going to be some composition that is let me do a subscript there. TiZN2. So the composition that's in this is just going to be 0.5. Over here, that's going to be basically, if you look at it here, let's just say like 0.65. Again, you could probably do the math on what the exact one is. Actually, it's 0.68. But anyways, you get the picture. we're basically running down from this point here. So we're looking at this composition right there. So what's the question actually asking us? So what's the composition? Great. What about the fraction? So we know if I'm here, if I want the fraction that's in TIZN versus the fraction that's in TIZN2, I'm going to use my lever rule. So the full length will simply be the concentration of TIZN, or basically, I'm just going to write it out numerically. It's going to be 0.68 minus 0.5, 0.68 minus 0.5. If I want the fraction that's in this phase right here, I do the lever rule, so I go opposite. So actually, I go 0.68 minus 0.55. If I want the fraction that is basically in here, I go the opposite. I go 0.55 minus 0.5. Clearly, we'll see this fraction is larger, which makes sense because I'm closer to, and we can zoom in here, I'm closer to this region here. So I should expect the fraction of my two-phase region should be larger in that TIZN phase. Relate the chemical potentials of each phase in the region. So if I'm in a two-phase region, the chemical potential of TIZN is equal to the chemical potential of my TIZN2. What are my degrees of freedom? So this is a binary phase diagram. So we're going to do Gibbs phase rule. So D plus P equals C plus 1. What are my components? 2. What are my phases? There's 2 phases in here. Degrees of freedom is 1. Makes sense. If I'm changing composition, I'm going to change essentially, or actually, if I change temperature here, I'm going to change my composition. If I change composition, I'm going to also change essentially basically the temperature at which these exist in. So they'll phase separate in this region. Excellent. So we got it. Any other questions here? Draw the free energy curves. Uh-oh. All right. So let's get started on this one. This is always the one of the more difficult parts of these types of problems. But it should be somewhat procedural after a time and after you get kind of used to it. So let's go ahead and actually, I'm going to use my, I wish I can kind of delete this, but I don't think it's possible to do so. But we might as well do this here. So this is my free energy. And what I see here is I have these certain points, and I'm going to draw these as these kind of lines here. So I'm going to go just up. Up. I'm going to go up here, and I'm going to go up here. So what's happening here? What is my phase in this kind of composition region? I'm just pure single phase here. Between here and here, I am BCC plus, what else am I? TIZN. I'm going to give these different colors. So I'm going to say this is this. I'm going to say, let's get us some nice different style. Let's see. I'm in a purple type of mood. I'm going to do this for this material. now I'm going to kind of just go bland. This for this guy, and then we'll do good old blue for liquid. All right, so let's kind of, again, let's go back and let's draw, or actually let's write out our phases. I'm sure there's a better way to do this, but if you haven't figured out by now in my videos, I am not a expert. So this is going to be this solid phase plus this solid phase. This is going to be this solid phase plus my liquid, and then here I'm just going to be liquid. So when I cross in these regions, and actually this is a little bit even more complicated because there's going to be an infinitesimal point here and here where we actually pass through a single phase region, but we're going to kind of ignore that somewhat. If you want to get technical, we'd have to draw an infinitesimally small at a single point where there's only a single phase region, but let's kind of ignore that endpoint for a second. So here, I am just going to draw to start off with, I'm going to draw arbitrarily my common tangents. And my common tangents, I'm going to make my common tangents orange. So my common tangents are where, again, I should expect to kind of see some commonality here. They don't have to all be the same. Oops, I knew that was going to happen. So let's do that here. Let's just kind of, I'm just going to draw some, again, they're completely arbitrary because we're not actually calculating explicitly, but my slopes have to be equal here. So I'm going to take the first free energy curve. We know lowest free energy wins. Do I have like a, it'd be nice if I could have like a, oh, I have 2 greens. We'll cancel this green out. So I'm low free energy here, and then it goes and hits, and then it goes up. If I want to now, I'm going to get my purple. Let's just go over here. I am going to be higher energy here, but I'm going to cross over. I'm going to hit. I have a common tangent slope between those 2 points because I'm in a 2-phase region here. And then this will hit up, slope up, and basically have a slope here, and then goes up. I'm going to change this let's just change this to gray. My gray is going to start over here. Again, common tangent, and then it's going to slope up. Actually, excuse me. We're going to need to, so I need the slope to be equal here, and then also hit there. And then finally, the liquid, which is my blue, is going to go here, here, and then just lower. So let's examine this. This is a single phase region. This is my lowest energy curve. This is a 2-phase region. Common tangent here and here. Equivalence chemical potential, because we know that the slope of our Gibbs free energy curve versus mole fraction is going to be approximately our chemical potential. So chemical potential must be equal. Same thing here. 2-phase region between this phase and this phase. We're good to go. 2-phase region here between this phase and this phase. Common tangent. Slope is equal here to the gray, here in the blue. And then single phase region. We got it. That's it. All right. Let's go on to the next one. Phase diagram. Again, I think that you all know this at this point, so if no one is, unless someone asks in the comments for the, again, it's going to be this phase plus this phase, this phase plus this phase, this phase plus this phase. Again, I think hopefully we can agree to skip that one. But if you want, I will create a separate video, but only if you ask. Okay, congruent melting points. Here, here, in this region right there. Where else? Do we see any? Here and here. That's it. What about some invariant points? There are some really cool ones in this problem that I really like. So let's go ahead and do it. What is this? Eutectic. Let's actually zoom in a little bit even further to make this easy. Where is it? Let's just focus on eutectics first. Eutectic. Eutectic right here. Any other eutectics? Not really. What about eutectoids? Where are my bunny ears? Where are my bunny ears? Where are my bunny? Ah, single phase region to what? Liquid, basically actually, this is a very interesting point. Actually, do we have, let's see if we have, actually, excuse me. So we're going single phase region to, ooh, actually, that's a very interesting point right here. I'm not sure if we have, no, these are also liquids as well. So this is actually not an invariant point, but it's a tricky one. So you see here, if this is, again, it depends on if this is gamma. So this is gamma plus liquid. So actually we go from here to here. So this would be a solid to a gamma plus a liquid. So that's actually not, that's not a transition essentially that we're going to be looking at here. What about peritectics or peritectoids? What's happening here? Solid to a new solid, peritectoid. Yes, that's exactly right. Nothing is really going on here. What about here? Solid, liquid, new solid, peritectic. What about here? Solid, new solid plus liquid to a new solid here, peritectic. What about right here? Solid plus liquid to new solid, peritectic. Excellent. Anything else? Nope, that's pretty much it. What else are we being asked to do? So now we need to look at 60% CE. So right here, we need to look at 400 C, which is right here. So again, we're in a 2-phase region of this and this. So what's happening here? So what's the composition? Composition of this is just basically 0.5. Composition of this phase is, let's see, 1, 2, 3, 4, let's say 0.76. And then that's my initial composition here. What's my fraction of this phase? So my fraction of this phase is going to be 0.76 minus 0.5. And then remember, I go opposite. So here, if I want to find the composition, I run here and then go back. But if I want to find the fraction, it's this fraction here. So it's going to be 0.76 minus 0.6. What's my fraction of this phrase? Again, same denominator, 0.76 minus 0.5. But now I run to the opposite. So I'm going to go to 0.6 minus 0.5. And that will be my fraction. Chemical potentials are equal. What are my degrees of freedom? It's going to be 1. We know that as well. Excellent. And then finally, at 1100, let's go to here approximately. What is my what's my free energy curve look like? So again, the key things, if we want to draw, I'm going to go draw from here to here. I need to draw from here to here, and then I need to draw from here to here, and draw from here to here. Oops, let me clear that up a little bit. And then here to here. So what do? Same as last time. So those are my, again, single phase, 2-phase region here, this, 2-phase region here, 2-phase region here, 2-phase region here, single phase. So I can just draw a common tangent. I could draw a common tangent, a little slope like that. I could do a common tangent like this, common tangent like going up like that, and then common tangent going up like that. So I could just pick, I'm just going to pick random colors. So again, single phase region here is just going to be here, up, and then gone. And then next phase, again, comes out, has to touch here, common tangent, has to touch there, common tangent, and then gone. Next phase, going here, again, touch the common tangent over here, touch the common tangent there, and then gone. And then let's go to another color. Again, over here, touch the common tangent here, touch the common tangent here, gone. And then finally the last phase. And then I don't know this is ugly, but I think that you get the pattern essentially from now. We touch here, and then again the common tangent is going to be, let's touch it right here, and then gone. There you go. And that's it. That is our P-Set 5. So excellent job. I will see you all. Again, common tangent, it's our chemical potential as well. So study hard for exam 1, and I'll see you in the next video. Thanks. Bye.